Okay, let's start our afternoon session in algebra. So it's my great pleasure to introduce Pham Tiep from Rajir University, and he represents also Vietnam Institute for Advanced Studies in Mathematics. He's first come to Brazil, so we should welcome here, right? And he's going to speak about representations of finite groups and applications.
Thank you very much. It's an honor and privilege to be invited to speak at the Congress. And I also want to thank my many collaborators with whom I have been fortunate to work with over many years. So I'd like to talk about the representation of finite groups and some applications. And I'm also lucky because many of the basic notions that I should have included in my talk were already given in the beautiful lecture that Jody Williamson gave this morning. Okay, but let me say something about the history. So probably many of you know that the representation theory of finite groups was born in the letter correspondence between Richard Dedekind and Frobenius in April 1896. And there were 3 letters from Frobenius to Dedekind on the 12th, the 17th, and the 26th of April in that year. Somewhat later, the foundation of the complex representation theory were developed by Frobenius, Dedekind, Burnside, Schur, Noether, and other mathematicians. And the foundation of the molar representation theory, it means that when you look at the representation of your group, but over the field of prime characteristic, where P divides the order of the group, were laid out by Richard Brouwer, started in 1965, and continued over the next few decades. Of course, you are wondering, this is such an old theory, right? More than one theory owned, and so what would still remain like an open problem to work on? Well, here's the main problem, or maybe a main problem. So given a finite group G and a field F, we'd like to describe all the illusory representation of G over this field F. And I should tell you that this problem is still wide open, even for your favorite groups, or maybe for my favorite groups. So I should tell you what are the favorite groups for me. Well, I like the symmetric group and the ordinary group. And I also like the finite group Lie type. So they are like the constant group defined over a vector space over a finite field, like the real linear group, the special linear group, the symmetric group, and also they are twisted and exception error. Why these groups are important? Well, one of the reasons is because of the classification theorem of finite segment group. And according to this theorem, so the group that I introduced above, and together with this 26 segment group, they account for the finite non-abelian segment group. Okay, so here's the main problem again. So let me just consider this problem on one example. So let's look at the group that we like very much, the symmetric group. So you know that there is a correspondence between the complex representation of Sn and the partition of n. So given any partition of lambda of n, then you can associate to it the complex representation and the character of that, which are denoted by chi upper lambda. And then, of course, we learn from our classes that you have the Hooke length formula to compute the character degree, and if you are given any permutation, then you can compute the character value at that permutation using, let's say, the Frobenius character formula. So it looks like we know everything about the representation of this symmetric group, right? Well, here's one example, one question. So what is the larger degree of the complex characters of Sn, like a function of n? And even by now, nobody knows what is the exact answer to this question. So the best result was due to Vershik and Kerov and Logan and Shep in 1977, but this result is asymptotic. So let me change the field a little bit. Okay, so now let me change the field to the smallest possible field, the field of 2 elements. So now we also have a bijective correspondence between the representation, between the illusory representation of G over the field of 2 elements and the so-called strict partition of n. This means that you divide n into some strictly increasing parts. So again, given such a partition lambda, then you can look at the corresponding representation. You can look at the Brown character corresponding to it, which I denoted by fiber lambda. So here's one question. So let's say that you take a n which is not too small, like 1,000. You pick a strict partition lambda, like the one that I chose randomly over there, and you want to ask, what is the degree of this representation? And I think we don't know. You can ask the same question for the general linear group of the matrices of size 1,000 by 1,000 over the field of 2 elements, and look at the representation over the field like 3 elements. And you can ask the same question, and nobody knows the answer. Even like a much easier question. So what is the larger degree of the complex representations of Gn n2, like a function of n, and what is the asymptotic of that function depending on n, when n tends to infinity? So this question was answered only recently in the work of Gunther Mahler, Michael Lassen, and myself. So I hope that I have convinced you that this problem is not an easy problem. Well, if we cannot do that, then let's make it easier. Okay, so here's the problem that we want to study. So given a group G and a field F, let me denote by d sub p of G the smaller degree of the feasible representation of G over the field F. And the problem is the following. So given a simple group G and a field F, you want to know what is the exact value of that invariant d sub p of G, and you want to classify the irreducible representation of G over F up to the square of that invariant. Well, the square looks like a random thing, right? And so we may think that this one, this problem, look like a very special instance of the main problem. But it turns out to be of importance, and also, if you can solve it, then it turns out to be efficient for many applications. Some of them I will talk about it later. Okay. So if you cannot classify on the irreducible representation of G, is there any way that you can find a good way to label them? So from the lecture of Jody this morning, we learned that for the Lie algebras or for the reductive group, we can use the weights to classify the representation. So the idea that Jonathan Alperin had was the following. So let's try to do the same thing for the finite groups. And here's the definition that he had. So if you have a group G and a prime P, then a P weight would be a pair Q comma delta, where Q is a P subgroup G, and delta is a character of the quotient, of the quotient of the normalizer Q by Q with the probability that it has P defect 0. Okay. And here's the conjecture. So the conjecture is that the number of the isomorphism classes of representation of G over F closure Fp should be equal to the number of G classes of P weights of G. Okay. So this conjecture would imply that we can try to classify the representation of the P molar representation of G by P weights. Okay. So in fact, this conjecture is just one of several fundamental conjectures in representation theory, and I should say all of them are still open until now. So we can have many more students. And many of those conjectures follow the global local principle, which in our case can be stated as follows. So certain global invariance of a finite group G can be determined locally in terms of its P subgroup, like the zero P subgroup, or their normalizers, and so on. So these conjectures include the Alperin weight conjecture, the Mackay conjecture, the Brown-Heisel conjecture, the date conjectures, and some other conjectures. Okay. Right. So we have some conjectures. So can I move it? Okay. Okay. So let me also give you the Mackay conjecture. This is probably the easiest one to formulate among all the global and local conjectures. And this conjecture was stated by John Mackay in 1971. So he said that if G is a finite group, P is a prime, and this the capital P is a zero P subgroup G, then there should be a bijection between the complex characters of G of degree co-prime to P and the characters of the normalizer P applicable prime to P. Okay. Later on, there have been several refinements which were due to Alperin, Mathematicians, Gabriel Navarro, Alexander Turun, and other colleagues. So basically, they say that we should be able to find a bijection pi which is compatible with the distribution of characters of G into P blocks with the action of certain Galois automorphism, with taking concursive modulo P, with taking log and sure indices, and so on. Okay. So we have discussed like 7 conjectures. So where do we stand, like talking about proving them? Well, those conjectures, they have been proved to hold for many families of finite groups, like similar groups, or maybe some simple group, but none of them has been proved to hold for all finite groups. But on the other hand, we know the classification of finite simple group. We know all the finite simple group. We know that the finite simple group, they are building blocks for any finite groups. So perhaps we can try to use the classification to reduce the conjecture to simple group. And I should say this was only one of the main ideas in the work of Eric Date in the 90s. But here's a caution. If we are lucky enough to find such a reduction, then we have to pay like a hefty price. We have to be able to prove much more about the simple group, not just the origin conjecture. So here's one reduction theorem. This is the theorem of Mathematicians, Gunther and Gabriel Navarro, which they proved in 2007. So they say the following. So let's fix the prime P, and suppose that you can prove that every finite non-abelian simple group S is Mackay good for that prime P. Then we know that the Mackay conjecture is true for all finite groups for the given prime P. Of course, what is this Mackay goodness thing? Well, so this condition is much more than just fulfilling the Mackay conjecture. In fact, I should say this is about 7 pages of their paper in the Invenciones. It's a long, complicated list of conditions on representation and cohomology of the group and some special subgroups. So you think it doesn't make any sense. Instead of trying to prove a very simple conjecture, now we are asked to prove much more about the simple group. But here's the good news. Right, okay, so the next sentence is, this theorem plays an important role in proving some further reduction theorem, but I want to go to the next one. Yes. Okay, so the good news is, in 2016, Guatemala and Rita Speth were able to prove the Mackay conjecture using the reduction theorem. So it shows that maybe this is a good way to do it. Okay. We talk about the Alperin weight conjecture. So so here's a reduction theorem for the Alperin weight conjecture that Gabriel Navarro and I proved. So again, we say that, so we fix the prime P, and suppose that we can prove that every finite non-abelian simple group is AWC good for that prime P. Then the Alperin weight conjecture is true for all the finite groups for the prime P. And again, this condition, the AWC goodness, is again much more than just fulfilling the Alperin weight conjecture, and it's about a page and a half of our article. A long list of conditions. I should say that a totally different reduction was proved by Louis Puch in the same, around the same time. So the question is, okay, so we want to show that every finite non-abelian simple group is AWC good. So which one are known to be AWC good? So, okay, so Gabriel and I, we show that the group of Lie type in the same characteristic P are good. Then Gunther Mahler showed that the alternating group are good. Then Zhang Wei Yan and Heiko Dietrich show that the sporadic simple group are good. So, well, these are the 3 families of simple group. So we seem to be done, right? But not quite, because I have 2 prime. So it remains to handle the group of Lie type, which are defined over a field of another characteristic. So there are 7 further reduction theorems which are proof for other global and local conjectures. So I should mention the reduction theorem of Britta-Speth. And also, if we want to talk about the Brown-High-Zero conjecture, one of the main conjectures in the theory, then we have the reduction theorem, which combines the work of Berger, Knorr, Navarro-Speth, and Navarro and myself. Okay. So now let me talk a little bit about the easier problem that I formulated at the beginning of my talk, the problem on the low-dimensional representation. So, recall that we want to determine the smallest non-trivial degree of the representation of our group, and also we want to classify all the representation of the illusory representation of our group up to the degree square of this invariant. So many of my colleagues have been working on this problem for the last, let me say, for the last 2 decades. So let me list some of their names: Bob Granick, Frank Himstead, Gerhard Hiss, Cornelius Hoffman, Gordon James, Sasha Kleshep, or rather Sasha Kleshop, Martin Liebeck, Frank Liebeck, Kai Pagard, Gunther Mahler, Alexander Zaleski, and myself. And some of the important tools or theories that we rely on are the Deligne-Lussig theory, some important results of Michel Brouet and Jean-Michel, of Cedric Bonafé and Raphaël Rouquier, and also some branching laws. Okay, so because of the technicality of this result, I'm going to formulate only 2 particular theorems. So let me go to the second theorem first, because the second theorem was proved before the first theorem. So this is theorem 2.4 proved by Bob Granick and myself. So we look at this special linear group Sn and Q, and we look at the representation of this group over the field of characteristic P not dividing Q. And we show that the smallest dimension of representation of this group over this field is this formula. So Q to the n minus 1 over Q minus 1 minus 1 or 2, depending on whether your P is not or is a divisor of Q to the n minus 1 over Q minus 1. And then we show that this group had exactly 1 illusory representation of that degree, and the P prime part of Q minus 1 of the degree Q to the n minus 1 over Q minus 1. And we can also show that all other non-trivial illusory representation of Sn and Q have at least the square of this D sub P of Sn and Q. Okay, so this is about the special linear group. And then the theorem 2.3 was proved very recently at MSI by Sasha Kleshep, Lucia Marotti, and myself. So we want to get a good upper bound, low bound on the dimension of the representation of the symmetric group. So we know that such a representation is labeled by some special partition lambda of n. So suppose that this partition is n minus m and some other part where n is not small. Then we show that then the degree of this representation is bounded from below by something which is roughly speaking like n choose m. So this is like a very effective bound. And for instance, if you use this bound, then we can prove some nice result on the let's say on the representation growth of the symmetric group. Previously, there was some low bound on the dimension of the moral representation of Sn, which were proved by Gordon James, and they are very nice, but they are only asymptotic. And now we do have an effective bound. Okay. So you see that in this kind of problem, so far we have been focusing on the degree of the representation. This means that when you look at the character of the representation, then you just focus on the value of that character at the identity. Now you can ask, what about the value at any other element? So, and let's try to do it for the complex characters. So here's the problem. Right. So the problem that I want to talk about is about bounding character values. Okay. So let S be a finite simple group and let G be any non-identity element in S. So I want to find an explicit and as small as possible constant gamma between 0 and 1, which may depend on G, such that the character ratio, namely the ratio between the absolute value of chi of G and the degree of chi, is bounded from the above by gamma for all the complex character chi of the group S. So this is about bounding the character ratio. And even better, and even more important for application, I want to find an exponential bound. Namely, I want to find an explicit and as small as possible constant alpha, which may depend on G between 0 and 1, such that the chi of G is bounded by the alpha power of chi of 1 for all the characters chi of the group S. Okay. Right. So here's a very important result in this direction, which was by David Glock, combining many papers in 1995. So he says that in the first problem about bounding character ratio, when you see that you want to find this gamma, right? And he said that 0.95 would do it. Now, what is the big deal, right? 0.95 is almost 1, right? But the fact that we can bound it away from 1 is very important for, and like I said, it took David Glock like a lot of efforts to prove it, and his theorem has been used many times in many papers. And I should say that this bound is true only, I mean, unless your S is a alternating group. Okay. Right. So let's try to talk about the second problem. So you want to bound the, we want to find an exponential bound on the character values. So first, look at the case where your group is a symmetric group. So the first important result in this direction was obtained by Sergei Fomin and Nathan Lulov in 1996, where they show that if all the cycle of the permutation G has the same size M, then chi is bounded by, roughly speaking, the M root of the chi 1. So this is a beautiful result, but the only thing is like it has this little O of 1. So they mean that you can use this only asymptotically. Some years later, Michael Larsen and Anash Shaleb were able to settle the general case of all the elements in symmetric group, and again their result is asymptotic. But only that result led to significant progress on many problems like mixing time, random walk, the very problem for the alternating group, and so on. So I am not going to talk about the sporadic group because there is only a finite number of them. So let's talk about the main division of the finite simple group. What about the finite simple group of Lie type? So it turns out that the convenient framework to work with them would be like to view our group S like the group of fixed point for some Steinberg anamorphism F on script G, where script G is simply connected algebraic group. So let me formulate the theorem that we proved recently together with Roman Bezrukanikov, Martin Liebeck, and Anish Shaleb. So we proved that there is a constant C which depends on the integer R with the following properties. So suppose that our group S comes from a simple algebraic group script G of rank R over a field of good characteristic P. And now let's look at any element G in S with the following condition. So suppose that the centralizer of G, I have to point to something, yeah. Okay, let me try to do it here. So we have this crucial condition that the centralizer of G in S is contained in something that we call a split Levy, meaning so we have some F-stable Levy subgroup of a proper F-stable parametric subgroup of G. And then for such a split Levy subgroup, we define the constant alpha, which is the maximum ratio between the dimension of the class of U in L and the class of U in G, where U is any non-identity unipotent element. Under this condition, then you can show that the character at G, the character value at G is bounded by C times the alpha power type 1. So, so most important for us is this term chi 1 to the alpha power, where your alpha is this explicit constant. So let me make some comment about this theorem. So the proof of the theorem relies on the linguistic theory, and particularly on the linguistic notion of universal support and the dual notion of wavefront set that was introduced by Kawanaga. And secondly, the exponent alpha in theorem 2.6, the one that I gave you before, is sharp. It can be shown to be sharp in many cases. But of course, the annoying thing is the condition that the centralizer of G is contained in this split-Levy subgroup. So we have been working on removing this split condition on L, and this is a work in progress with Rahman Bezulkadukov, Guatemala, and Jay Taylor. So we hope that we'll be able to remove it. But even if you can remove it, then you can see that our theorem doesn't cover all the elements in the group. So fortunately, for type A, if our group is a special linear group, then we can prove a bound which is true for all the elements in the group. So basically, it says that the character value is bounded by the 1 minus 1 over 2n power of type 1. So you see that we spend a lot of time to go down from 1 to 1 minus 1 over 2n. But that's important for many purposes. I also want to mention another bound, which was also proved recently by Bob Granit and Michael Larsen and myself. So this is a different kind. So we proved that for any epsilon between 0 and 1, there is a delta such that we have the following statement. For any finite simple group of Lie type, whenever we have an element S, where the centralizer, where the order centralized bounded by the delta power of the order of S, then the character value is bounded by the Fn power of chi 1. And for instance, if your S is like SL or SU, and if your epsilon is like 8 over 9, then you can take your delta to be something like 1 over 12. Okay. So now let me try to discuss some application. So the result that we proved have been used in various applications in and outside of group theory. But today I want to talk about 3 specific applications. So the first one is in number theory. So probably we only learned from the talk of Jack Thorne yesterday about the proof of the implicitly about the proof of Andrew Wine of Fermat's theorem, which relies on the leading theorem proved by Richard Taylor, Andrew Wine in 1995. I'm not going to spell out this theorem, but I just want to say that it says that under certain conditions we can lift the modularity of the reaction mode P of the Galois representation to that of the representation itself. Okay, so from phi bar to phi, and we have the condition that the image under the Galois, the image under the phi bar of some Galois group is big, and here the bigness it just means to be irreducible. Okay, so later on in 2010, Michael Harris, Nick Shepard-Barron, and Richard Taylor proved a very important case of the Sardo-Tate conjecture, and this time they relied on another leading theorem where we just replaced the Gn2 by Gn and modularity by automorphy. And now the bigness condition is much more than just irreducibility. And then in 2012, Jack Thorne derived further the leading theorem of Clausen and Harris and Taylor, replacing the bigness by adequacy. So here's the definition of the adequacy. So if you have a fin F of characteristic P and you have a G, which is a finite irreducible subgroup of GnV, then suppose that we have 3 conditions, that the H1, this first cohomology group of G with coefficient in F is 0, and the H1 of G with the coefficient in N of V mod the scalar transformation is also 0. And the third condition is that the space N of V is spanned by the P prime element in G. Then you say that G is adequate. Okay. And this is a technical but important definition. But let me tell you that the game is to try to show that maybe all or most of the finite illusion subgroup of G and F are adequate. If we can do that, then in the lifting theorem, we don't have to say that the subgroup is adequate. We can just say that the subgroup is irreducible, like we had in the theorem of Taylor and White. And it's easy to show that UP doesn't divide the group order, then G is adequate. But it's much harder to show that EOP is large enough, like at least 2 times n plus 2, then G is also adequate. And this was a result of Bob Grant, Florent Herzig, Taylor, and Thorne in 2012. And this result has already been used to prove some new lifting theorem. So here's the theorem that Bob and Florent and I proved. So we say that, suppose that you have a finite illusion subgroup. Let's look at G plus, which is a subgroup generated by all the P element in G. And suppose that V, like a G plus model, has a simple submodel dimension less than P. Then, aside from a couple of examples, we know that your G is also adequate. And the tools that we developed along the way of proving this theorem also allow us to answer some questions of Jean-Pierre Serre and Billy Mazur. But to save some time, let me go to the next application. So this is about the invariant that Gangtian defined in 1987 for any Kähler manifold and any complex subgroup of automorphism of X. And Tian uses invariant to prove the existence of invariant Kähler-Einstein metric on X in some important cases. So the case of interest to us is a case where G is a finite group acting on the projective space. And then, in this case, the alpha invariant is also known to the algebraic geometers like the log canonical threshold. But it turns out that in 1981, John Thomson already proved that if you have a finite subgroup of G and C, then the alpha invariant of this projective space is bounded by 4 times n. So of course the question is like, how could John Thomson prove something that wasn't defined at that moment? Well, here's the explanation. So it takes a lot of effort to prove this theorem, but also to press the button. It doesn't move at all. Okay, Okay, so we say that a group G has a semi-invariant ability K on V if the K symmetric power of V contains a one-dimension G submodule. And let this of G denote the smallest degree of the semi-invariant. Then the connection was shown to be the following, and it was observed by Vanya Chensov and Kostya Shramov. So they show that the alpha invariant of the PV is bounded by D of G divided by the dimension of V. So actually, John Thomson proved that the D of G is bounded by 4 times n squared. And if you divide by n, then you get the bound for the alpha invariant. Now, in the same paper, John Thomson said that, well, instead of this linear bound, we should have a universal bound. So this means that there should be a constant C such that the alpha invariant is bounded by this C, and the small degree of the semi-invariant is bounded by C times n for all the finite subgroup G of G and NC. Okay, so the alpha invariant should be universally bounded for all n. And here's the theorem that I proved. I proved that Thomson conjecture holds for some C, which can be taken to be 1,184,036. Okay, and with that constant C, then we can also show that any finite subgroup G of G and C emit an invariant of degree C at most C times n times the index of the G prime, the derived subgroup in G, and where C is something like 1 million. So with more effort, one can try to drive down the C to something like maybe a few hundred. But we believe that the right value for C should be something like 12 or so, but we don't know how to prove it. Okay. So now, let me spend some time to talk about the third application, which is about the random walk and word maps. So what is word map? Well, so let FD denote the free group on D letters, x1, xd, and let W be a non-trivial element of this group, and let G be any group. So by word map, we mean a map W from G upper D, the Cartesian product, to G, where you send any D tuple to just a value at W, and then the image would be the image of this W on G upper D. So the non-commutative varying problem, which was studied by the papers of Efim Zermanov and Jan Saxon and John Winson, is the following. So let W be a non-trivial element FD in the free group, and let G be a simple group. So we want to know how large is the image of this word map, and assuming that the image is non-trivial, you want to know what is the width of W, which is defined to be the smallest k, such that the k power of the image covers everything in G. And also, in a more precise way, you want to know how close is the induced distribution PWG to the uniform distribution on the group, where this PWG is defined to be the ratio between the size of fiber divided by the size of G upper D. Okay, so what can you say about this problem? So it's a theorem that Michael Larsen, Anne Shalab, and I proved. So suppose that W is a product of two disjoint words, W1, W2, which are non-trivial, and let G be any finite simple group. So if the order of G is large enough, then you can show that the word map is always selective. So this means that the image is the entire G. And this implies the second statement that if the order of the simple group is large enough, then any non-trivial word map W1 has width 2. And the third statement, so we show that when the order of the simple group tends to infinity, then the induced distribution is almost uniform on G in the N1 norm, meaning that if you take the N1 distance between the induced distribution and the uniform distribution, that it tends to 0 when the order of G tends to infinity. So this, in some sense, this is the best that you can do with the general word maps on simple group. But you notice that in all this statement, I have the condition that the order of G has to be large enough. So it means that we know that something is true, but far away from the A5 or A6 from the small simple group. So you want to have something which is true for all the simple group. Okay, so let me give you some. Oh, right. Okay. Some word maps that are selective on all simple group. So the first one is the commutator word. So this was known as the Ore conjecture, and now it's a theorem due to the many work done previously, and then finally by Martin Liebeck, Eamon O'Brien, Anne Shalab, and myself. So this theorem says that every element in any finite simple group is a commutator. So the next example is, well, now you can take N to be any product of two prime powers, like P to A, Q to B, and then the word map X to Z, Y to Z is selective on own simple group. It means that every element in any finite simple group is a product of two N powers. Well, from this theorem, you can deduce the Bernstein theorem in the wrong way, but you can deduce it. Now, oh, I forgot to say that, well, it is on the slide that it was proved by Bob and Martin, Eamon, and Anne and myself. We also proved the next result, which say that if your N is any odd integer, then the word map X to Z, Y to Z, Z to Z is selective. meaning that any element in any finite non-reducible group is a product of 3 n powers if your n is odd. So in the second statement, we have 2 powers. In the third statement, we have 3 powers. And we can show that these are 2 and 3, they are sharp. So it can go down to 1 or 2. Okay. Right, so now let me talk about the random walk. So what is a random walk? So suppose that you have finite group G and you have a set of generators S, then you can define the Cayley graph where the edges, where the vertices are just the element in G and the edges are labeled by the by G comma GS, where S is the element in the generating set. So here's the random walk on gamma. So we start from the identity, and at each step we go along the graph, but choosing the next edge uniformly with probability 1 over the size of the S. And we want to study various things like, for instance, the missing time. So you want to reach every vertex like almost uniformly. So you want to know what is the minimum number of steps that is required to reach an almost uniform distribution. And here's the exact formula for the missing time. So this topic started from was started by the famous paper of Percy Diaconis and Jashani in 1981, where they studied the random walk, where the set of generators is the identity and the transpositions. And later on in 1992, Hildebrand studied the case where your G is SN and Q, and the S is the set of transposition. So using the result that we prove, we can show the following. So if you take the SN and Q and you take any non-central element, then the random walk defined using this class of X has missing time at most 2 times n plus 3 if Q is large enough. So you should compare it to the result of Hildebrand, where we have the transposition, and then over there the missing time is like about n. Here's another corollary of our result. So with Bob and Michael, we show that there is a positive constant gamma such that for any finite simple group Lie type over FQ, and if you use an element X with not too big centralizer, so at most the order of G in the power gamma, and if Q is large enough, then if you look at the Cayley graph defined using this class, then the Cayley graph has the diameter at most 3, and the random walk on this gamma has missing time 2. Now I should say that this theorem 3.8 confirms a conjecture of Alex Lubotsky about the relationship between the diameter and the missing time on the Cayley graph. So because I have 2 minutes, so let me also talk about another kind of random walk. So this is random walk, but on group representations. So now, again, our G is a finite group. Alpha is a fixed faithful character. So then we define the following graph, gamma G alpha, where the vertices are the irreducible representation of G, and the edges are the pair chi phi, where phi is a constituent of chi alpha. And then you can define a random walk on gamma. We start from the identity representation, and at each vertex we choose the gamma. At each vertex chi, we choose the next edge with this probability, which is like you can see that this is the ratio between the dimension of the homogeneous component corresponding to phi, if comparing to the degree of chi 1 times alpha 1. So the random walk on complex representation have been studied by Jason Fullman and later on by Percy Diaconis. So this spring at MSI, so we started to work on the random walk on moral representation under the influence of Percy Diaconis. So there is a work in progress with Georgia Benkart and Martin Liebeck, and also Martin and Anne and I, we also look at this from another angle. So we prove some result on the coming number, which can be rephrased like the diameter of this graph gamma. Okay, so at 20 seconds, so I should stop here.
Any questions? Well, if no questions, let's thank speaker again.
Thank you.